Hello everyone, welcome to my channel. So in this video I'm going to discuss the second part of the current electricity topic. So basically I'll be discussing Ohm's law, then resistance, then the concept of drift velocity. So starting with Ohm's law, now before I discuss this topic, let's see one example. Suppose you have a pipe, okay, and this pipe is connected to a pump, okay, and this pump is pumping some fluid in this pipe. Now the rate of flow of fluid in this pipe will be more if the pressure exerted by this pump is more. So greater the pressure exerted by the pump, greater is the rate of flow of fluid in this pipe, okay. Now correspondingly, suppose you have a conductor, okay, with some resistance R. Now greater the applied potential, greater is the strength of current flowing through this resistor, okay. So greater this, more the potential, more the current. So one way of stating this Ohm's law is the ratio of voltage to current is a constant, provided other physical conditions are constant like temperature, pressure, all these things. If they are maintained constant, then the ratio of voltage to current is a constant. That is Ohm's law. This is one way of expressing Ohm's law. The other way is the strength of current flowing through this conductor, it is proportional to the potential difference. Is proportional to the potential difference. Greater the potential difference, greater is the strength of current flowing through this conductor, okay. Now this R is the resistance of this conductor, okay. Now so if V by I is a constant, okay, now what is this constant? This constant is called resistance. R is the resistance. Now in this case it will be I is equal to 1 by R into V, or I can write V is equal to R into I. So this is the mathematical form of Ohm's law. V is equal to R into I. Applied potential is equal to resistance into strength of current flowing through the conductor. Now as you can see, this R resistance is the proportionality constant. R is the proportionality constant. In this case V by I, this R is constant, okay. Now wherever, whether it is in physics or in mathematics or in any science, if wherever you have this constant term, now this constant term will be independent of V and I, okay. So this R, it is independent of V and I, okay. This is true for any mathematical relation. Suppose you have A is proportional to B and A is equal to K into B. So this K will be independent of A and B. That is why it is called proportionality constant. That constant is independent of other two terms. Similarly, R is independent of V and I. It may depend on some other terms. Similarly, this K may depend on some other terms, but it will be independent of A and B. Similarly, R is independent of V and I. Okay. Now, if R is independent of V and I, then on what factors does this R depend? Okay. So next, let us see the factors on which this R depends. Now as you have already studied in class 9 and 10, that this resistance of a conductor depends on length and area. We write R equal to rho L by A, where rho is the resistivity, L is the length of the conductor, and A, capital A, is the cross section area. Now let's see, check this dependence. We will verify this dependence, okay. Now suppose we have a conductor. So this is the conductor, okay, and this A is the cross section area. This area is A, and L is the length of the conductor, okay. Now for this conductor, if V is the applied potential such that I is the current flowing through this conductor, so in that case we can write R is equal to V by I, okay. Now suppose if I take two identical such conductors and keep them in series. So this is one conductor and this is another conductor. So these two conductors are of same material, identical to this, and they have same dimensions. Materials is also same, so cross sectional area is A. So this length is L, this length is also L. Okay, now for this combination, let's say RC is the resistance. Okay, now see, potential drop across this part is V, current is I. Now these two are in series, so same current will flow through them. So potential drop across each part, for this part potential drop is V by I. For this part again potential drop is V by I. So total potential drop will be V by I plus V by I. So that is equal to, so this, see, this part potential drop is V, this part potential drop is V, I is the strength of the current, both are in series. So this part resistance is V by I, this part resistance is V by I. So V by I plus V by I, that is equal to 2V by I. But what is V by I? V by I is R. So 2V by I will be equal to twice R. Okay. So that means, see, when you increase the length by double, so this is L, this is also L, the resistance also doubles. So this means resistance is directly proportional to L, length. Okay. Now suppose if I cut this conductor such that I have half the area, so this is A by 2. If I slice this in this direction, okay, so this is A by 2, length remains same, and if I take two such elements, so this is again A by 2, length is L, this is also L. Okay, so now this current, see this current, so I have sliced this in this part along the length. Okay, so as that this part is area A by 2, this part is also area A by 2, A by 2, A by 2. So this current which I flows through this conductor now gets divided into two parts, one part going from the upper segment and one part going through the lower segment. Now since both the segments are identical, so equal current will flow through them. So I by 2 current will flow through this part, I by 2 in this part, I by 2 in this part. Net current is I. Okay, so resistance of each part, in this case say R dash is the resistance of each part. So in this case, see, potential remains same. So this is the same conductor, but it has been sliced by along the length. So potential is V, current still remains I. So half current flows through upper part, half current flows through the lower part. So for one segment, if the resistance is R dash, okay, for one segment if the resistance is R dash, applied potential is V, so this is equal to V, current, so potential across this is V, potential across this is also V. How much current is flowing? I by 2, so this is I by 2, so this is equal to twice V by I. Okay, so now we have seen, so this is the resistance of one segment. Okay, for this resistance is R dash, for this again resistance is R dash. So as you can see that when the area is halved, the resistance has increased by 2 times. R is V by I, R dash is 2V by I. So when the area is halved, resistance is increased by 2 times. What does this show? This shows that this resistance is inversely proportional to area. Okay, so here you have resistance proportional to L, here you have resistance inversely proportional to area. So if you combine these two results, what do we get? We get R proportional to L by A. Okay, so now if you remove this proportionality symbol, we have R is equal to rho L by A. Okay, now so this rho is called resistivity. Rho is called resistivity. So as I told you, see, this proportionality constant will always be independent of other terms. So that means rho will be independent of R, L, A. Okay, so rho, it depends on the nature of material. Rho, it depends on nature of material. Depends on nature of material. Okay, it is independent of dimensions. It is, rho is independent of L and A. Independent of dimensions. Okay, so these are the few things with regard to the resistance of a conductor. So from Ohm's law we have V is equal to R into I. Okay, now just now we have seen that resistance, it is related to length and area by the relation R equal to rho L by A, where rho is the resistivity. Okay, so if I substitute this value of resistance over here, I get V is equal to rho L by A into I. Okay, now this can be rearranged as V is equal to I by A into rho L. Okay, now let us define a term called current density. Current density. Okay, now it is a vector quantity denoted by the symbol J. Okay, small j with the vector symbol, it is a vector quantity. Okay, now how do we define it? Suppose you have a cross sectional area like this, okay, such that this is the area vector and current is flowing in this direction. Current, it is flowing in this direction. This is I, such that this angle is theta. Okay, so the component of area vector in the direction of current is A cos theta. So A cos theta is the component of area vector in the direction of current. Now current density, it is defined as ratio of current to component of area vector in the direction of current. So J is equal to I by A cos theta, or I is equal to J dot A. Okay, so current, it is a scalar quantity. Okay, current is scalar, but current density, it is a vector quantity. It is a vector quantity. Okay, so basically current vector, it is current density. You can simply say if this cross in normal conductor, if for a normal conductor, this area vector will be in this direction, current will also flow in this direction. So in those cases, these are simple cases. So for such cases, current density is simply current per unit area. Okay, current per unit area. So this I by A, can be replaced by current density J. So that I can write this expression as V is equal to J rho L. Okay, now suppose this is a current carrying conductor. V is the applied potential, L is the length, and E is the strength of the electric field inside the conductor. L is the length of the conductor. So this strength of the electric field, potential and length of the conductor, they are related by the relation E is equal to V by L. Okay, strength of the electric field, potential and length. This is the relation between, in the chapter electrostatics, you have studied that electric potential or electric field is negative gradient of electric potential. Electric field is always directed in a direction in which electric potential decreases. So from that concept I have written E is equal to V by L. Okay, so that V by L, it will be J into rho, or V by L is E, so you have E is equal to J into rho. Okay, or I can rearrange as E is equal to rho J. So this is another form of Ohm's law. Okay, that is strength of the electric field in a current carrying conductor, it is directly proportional to current density, and the proportionality constant is resistivity. Okay, so this is another form of alternate form of Ohm's law. So E equal to rho J. This can also be written as J is equal to E by rho. Now 1 by rho, resistivity, reciprocal of resistivity is conductivity. So J is equal to sigma into E. Okay, so these are the two alternate forms of Ohm's law in addition to the normal form V is equal to Ri. So next we will try to understand the term drift velocity. drift velocity. Okay, now as we know that a normal conductor has large number of free electrons, and these electrons are in a state of random motion. They are moving in all different directions. Now suppose this is the path taken by one particular free electron. It goes like this, then it goes like this, it undergoes collision, then it moves in this direction, undergoes collision, then goes to this point, undergoes collision, and finally it reaches here. So this is the path traced by one particular free electron. Okay, and now electric field is applied in this direction. Electric field is applied. So this is the path traced by electron in the absence of electric field. Okay, and now this electric field is applied. Let me make it red color. So now electric field is applied. Okay, now we know that this electron being negatively charged, it will be drifted or in a direction opposite to electric field. It is negatively charged. Positive charge always moves in the direction of electric field. Negative charge always moves opposite to the direction of electric field. So in the direction, see, electric field is directed in this direction. So electron, it will be drifted slightly in the opposite direction, opposite to the direction of the electric field. So it will take this path. Okay, so this is the dotted line, that red color line. This is the path traced by the electron in the presence of electric field. Okay, so what does this mean? See, when there is no electric field, all the electrons, they are in a state of random motion. Okay, so when there's in a state of random motion, the average velocity of the electrons, free electrons, will be 0. So when electric field is 0, the average velocity of the free electrons, 1 by n sigma I equal to 1 to n vi is equal to 0. So this is the average velocity in absence of electric field. Okay, now on application of electric field, what happens? So the acceleration of the electron is F by m. So that is equal to force by mass. So force is minus E charge into electric field divided by m. Remember, F is equal to QE. F is equal to Q into E. Charge of electron is minus E. E is the strength of the electric field. Okay, so this is the acceleration. Okay, so if I use the equation of motion, V is equal to U plus AT, and we take the average value. Average value of final velocity, average value of initial velocity, average value of time. So V average is equal to U average. Initial average velocity is already 0. So 0 plus minus EE by m into tau. This average time tau, it is the average relaxation time, that is the time interval between two successive collisions. So this is the average relaxation time, that is time interval between successive collision, because it will acquire this velocity only for one particular time till which it undergoes collision. After collision, the velocity will again change. So this is V average is equal to minus E, if I write this in vector form, this E by m into tau. Okay, so this is the average velocity, and this average velocity is called the drift velocity, average velocity of the free electrons in the presence of electric field. So we have Vd is equal to minus EE tau by m. So as you can see, the only vector quantity here is drift velocity, here the vector quantity is electric field. In between you have a minus sign. That means that is the drift velocity, the direction of drift velocity of free electrons is opposite to the direction of electric field, this minus sign shows that Vd and electric field, this is the vector quantity, this is the another vector quantity, so these two vector quantities are in opposite direction. So drift velocity of free electrons is opposite to the direction of the applied electric field. Okay, now next we will see the relation between current, strength of current and drift velocity, strength of current and drift velocity. Okay, so suppose you have a conductor, and across this conductor we apply a constant source of potential V. Okay, so the free electrons, they are drifting in this direction with drift velocity Vd. Okay, now number of free electrons, let n, small n, be the number of free electrons per unit volume. Number of free electrons per unit volume, it is equal to n, small n. Okay, now if Vd is the drift velocity and t is the time taken to travel through this conductor of cross-sectional area A. So if Vd is the drift velocity and t is the time taken to travel across this cross section, then Vd into t will be the length, A is the cross section. So in that case, so Vd into t into A will be the volume traversed by the electrons per unit time. Okay, so that number of free electrons, that total number of free electrons, if it is equal to capital N, it will be equal to n, number of electrons per unit volume, into the volume traversed per unit time. So that is n into Vd t into A. Okay, now from quantization of charge principle, you have Q is equal to Ne. Charge total, Q is the total charge on a body. So charge on a body is equal to the integral multiple of elementary electronic charge. E is the charge of electron, N is the number of electrons. So this is quantization of charge. Quantization of charge. Okay, so you have Q is equal to N V dt A into E. Okay, now Q by T will be equal to N A E V D. Now what is this Q by T? Q by T is the strength of the current. So that we have I is equal to N A E V D. So this is the relation between current and drift velocity. Okay, now we have already seen that drift velocity, it is equal to E tau by m in scalar form. In vector form, when you have a minus sign. Okay, so this is the magnitude of drift velocity. So if I substitute this value over here, I get I is equal to N A E E tau by m. Okay, now rearranging these terms, I can write I by A is here, so is equal to N E square by m E tau. Okay, now what is I by A? I by A is current density. Okay, so current density, this can be written as I by A is J, so J is equal to N E square tau by m into E, or I can write E is equal to m by N E square tau into J. Now Ohm's law, we had E is equal to this form, E equal to rho J. So that means this quantity m by Ne square tau represents rho, resistivity. Rho is equal to m by Ne square tau. So this is the expression for resistivity. Okay, or conductivity is reciprocal of resistivity. So conductivity sigma can be written as Ne square tau by m. This sigma is conductivity. This is conductivity. conductivity. Okay. So next we will study a term called mobility. Mobility of charge carriers. It is denoted by the symbol mu. Now mobility of charge carriers, it is defined as magnitude of drift velocity per unit electric field. Okay, it is defined as magnitude of drift velocity per unit electric field, per unit electric field, per unit electric field, magnitude of drift velocity per unit electric field. So mathematically I can write it as mu is equal to Vd, this is magnitude of drift velocity per unit electric field E. Okay, or I can write simply as mu is equal to Vd divided by E. Okay, so this is the mathematical form of mobility, expression for mobility. Now see this drift velocity, if we see the unit of this mobility, drift velocity is meter per second and this electric field is volt per meter. Okay, so the unit of mu or mobility, it will be meter square per volt second. Okay, and this mu is a positive quantity. Okay, it is a positive number. Mu is always positive, always positive. Okay, now see this, for expression for drift velocity we had magnitude of drift velocity Vd is equal to E tau by m, charge of electron, electric field, strength of electric field, average relaxation time divided by mass of the electron. So that I can write Vd by E as E tau by m. So if I substitute this over here, I have mu is equal to E tau by m. So this shows that mobility is inversely proportional to mass of the charge carriers. Obviously, greater the mass, less will be the mobility. Smaller the mass, greater will be the mobility. Okay, mobility of electrons is far greater than mobility of holes. Okay, mobility of electrons is greater than mobility of holes. Electrons are the charge carriers in conductors, holes are the charge carriers in case of semiconductors. That we will study in the chapter semiconductor electronics. Okay, so these are the few basic things related to drift velocity, mobility, Ohm's law and resistance. So this is based on your NCERT textbook. So my advice is please go through, after watching this video, also go through your NCERT textbook, have a good understanding of all the concepts. Write these things, after understanding all the things, write the things on your own, all the concepts on your own, so that these concepts are as strong as concrete in your mind. Okay, good luck.